Okay, guys, so real quick, let's just think about this problem before we actually do anything. We have a parametric equation for this line integral, and you guys can see that if I put in cosine t here and sine t and z sine t of all that stuff in here, I don't know if it's going to be much easier, right? Like, I can get this line integral, and it'll be kind of a big line integral, maybe even hard to do, or maybe everything cancels out nicely. But we do know that it's a line integral, and it goes from 0 to 2 pi. So whatever the shape would look like, let's just say in the x and y plane. So in the x and y plane, I already know that's going to look like a circle from 0 to 2 pi. Like, I literally know that because that's what, this is the polar. And it's from 0 to 2 pi. So just in the x and y plane, I know this. And then if I know that this is a line integral, so f dot dr, right, if this is a line integral, and it's closed, and if f is conservative, right, if f is conservative, then there is some scalar function del f, well, some scalar f, and you take its gradient del f, and then it would be the same thing as this, right, del f dot dr, and then you can imagine from this then, right, that we know that this is what? I'll just say this is from b to a, the f of b minus f of a, right? And if f of b and f of a are the same thing, if, for example, f of b is equal to f of a, as where we can see that 0 and 2 pi are the same point, right? They were just numerically different, but they are the same point in terms of position. Well, then if the same thing minus the same thing, well, then we know that f dot dr is equal to 0, okay? So I'm arguing that this is equal to 0. Now, there's another way to find out that this is equal to 0. It's mainly just a different way to find that the field is conservative. So usually what we do, what you did before, is you go dp dy is equal to dq dx, and then you say conservative, right? However, that doesn't look very nice for 3-dimension, right? But what you can do is you can take the curl of f. And if the curl of f is equal to 0, then it's also conservative. So if we take the curl of this, let's see. If we take the curl of this, and if the curl is equal to 0, then the integral is equal to 0. And we know that because of this theorem. F dot dr is equal to the double integral curl f dot ds. Okay. And what theorem is this? This is Stokes' theorem. Okay. So the reason why I'm doing all this stuff over here and just showing you this is because I don't want you to ever do this type of math. I want you to realize the theorems so you don't have to do the crazy nonsense minute math. Okay. Now all I want to do is take the curl. And the curl is equal to the gradient cross f. And we can write that, oh, one second, let me just bring this guy down a bit. That is equal to this determinant vector, so we say dx, dy, dz, so operators, dx, dy, dz. And then we get p, q, and r. And the reason why I write p, q, and r instead of this stuff in here is because I want my life to be easier. Now I could call this p, q, and r. And then if you guys see, if I take this cross product, what I get r with respect to y. This is a y here. Let me make it look more like a y. So I get r with respect to y, and then I get q with respect to z, and I minus them. And then I get r with respect to x, and p with respect to z. And then I get q with respect to x, and I get what? And I get p with respect to y. It's kind of funny. It's like this part. As where you see that Stokes' theorem is the big brother to Green's theorem, right? And this is using Green's theorem. Okay, now if I actually compute this stuff and I give it a lot of space, so I'm going to take r with respect to y. If I take this to respect to y, it's going to be negative 2y cosecant squared z. And then if I take q with respect to z, what do I get here? So if I take it with respect to z, well, this is 0. I take this with respect to z, it's going to be 2y. And cotangent it becomes negative cosecant. So now I'll write negative cosecant. It becomes negative cosecant squared. So as you guys can see that this cancels out here. Sorry, it's kind of clunky. But they do cancel out. Okay, what's the next one? Okay, and then if I got r again, I'm going to take it with respect to x, you see that's 0. And if I take p with what? P with respect to z, then this is equal to 0. Okay, and then if I take q with respect to x, this is 0, but then this is still part of q. If I take it with respect to x, it's just going to be 4x e to the 2y. Then it's going to be minus, and p with respect to y. Let's take p with respect to y. Look at that. That's going to be 4x e to the 2y. And those cancel, and this cancels. Everything cancels. Isn't that nice? So the curl of the curl of f is equal to the gradient cross f, which is equal to 0. So then our field is conservative. So we say this, right? We say if f dot dr is equal to the double integral curl f dot ds. And then if we see that the curl of f dot ds is equal to 0, then we're integrating 0 dot ds, which is equal to 0. So there we go. I mean, guys, like please, read the textbook so you don't have to do these problems. And real quick, just if you don't believe me, I do have Chegg, and I want to show you what happens. I'll show you what happens. So this is what they do. Look at that, man. I don't think anybody wants to do this. This is ridiculous. How many integration by parts are they doing? I mean, look at all the substitutions. And look, it goes to 0. So as you can see, it's important to read and understand what the textbook says and know when to use certain theorems, right? So instead of using a line integral and converting it with all this stuff and doing a giant integral, you should just read the textbook and see what Stokes' theorem says, and then if you should read the textbook on what the curl, so if you read that the curl of f is equal to 0, that means the field's conservative, and then you go back a chapter, and then you see that, right, by the fundamental theorem of line integrals and by Stokes' theorem, everything is telling you that this is equal to 0. So there we go.